In this experiment, we observed three identical cans descending a 25-degree inclined plane. One is empty, another contains water at room temperature, and the third contains frozen water.
When released simultaneously, the result is clear. The can with liquid water arrives first, followed by the one with ice, and the empty one comes in the last. Although the ice can and the water can have exactly the same mass, their dynamic behavior is completely different.
The key to this phenomenon is the moment of inertia, which is the resistance an object offers to changing its state of rotation. It's a can with ice, the contents are a solid block attached to the aluminum. As it descends, all that internal mass is forced to rotate.
In contrast, in the can with water at room temperature, something fascinating happens. The aluminum walls rotate, but the liquid inside practically doesn't rotate. Due to low friction, the water simply slides down while the exterior rolls.
This is explained by the principle of conservation of energy. The potential energy the cans have at the top transforms into two things as they go down: translational kinetic energy, which makes them move forward, and rotational kinetic energy, which makes them suspend.
Since the can with liquid water doesn't spend energy rotating the mass of the liquid, almost all its available energy is converted directly into linear velocity. That is why it accelerates much faster than the others.
On the contrary, the can with ice spends a significant part of this energy making them very solid. Rock spins on its own axis. Automatically, this reduces its linear acceleration to 67% of its maximum potential.
And what happens to the empty can? Being a hollow cylinder, it has all its mass concentrated on the outer aluminum edge. This geometric distribution gives it the highest possible moment of inertia in proportion to its mass.
Result: the empty can wastes 50% of its energy solely on managing to rotate on itself, leaving it lagging in last place. In conclusion, on an inclined plane, the heaviest object doesn't descend fastest, but rather the one whose mass distribution minimizes its resistance to spinning.